Hello, dear members. Thermodynamics class, you're so much welcome. Now, we are going to discuss fuels and combustions, and this is going to give us an introduction as we handle sub-module 5. And I believe by the end of this lecture and at the end of sub-module 5, everyone should be able to understand what a fuel is, what is combustion, and then how can you differentiate between the different fuels, the solid, liquid, and gaseous fuels. How can you calculate the uh, enthalpy of formation if it is asked of you? How can you determine the amount of air required for complete combustion of the fuel? How to determine any excess air that did not take part in the combustion of the fuel. I believe everyone should be able to enjoy. Kindly, if you don't understand anything, I would advise that you follow this lecture with a pen, a book, and note down the things you are going to be seeing here, the key points. Then also those that you don't understand, you can put them in the description, I mean in the comment box, so that I be able to find them in my YouTube channel. Remember to share, like, and subscribe so that I be able to serve you better. So let's rush directed to this lecture. We are going to look at classification of fuels by state, their characteristics, storage, and handling. So classification by state, we are going to look at solid fuels first, and this involves coal, wood, charcoal, peat. But what is most common here to you, I think it's wood and charcoal. The characteristics of solid fuels is that they have high energy content, they require more handling, that is, they come in large quantities, and so they become bulky. They tend to become bulky, and they also require a lot of space to store. They also produce a lot of ash. Then the storage and handling, we have already said, they require dry storage to prevent moisture absorption. That is in addition to what we have already said. And then you also need proper ventilation to avoid spontaneous combustion. So let's look at the liquid fuels also. And these include, but not limited to, petroleum, diesel, kerosene, and fuel oil. What is common to you, I think, is petrol, diesel, it's kerosene that you use in your lamps for heating, for lighting, and also the diesel and petrol run engines, the internal combustion engines for driving or propelling automobiles. The characteristics is that liquid fuels have high energy density. They are easy to transport because you can put them in cylinders, in containers, and then be able to transport them at longer distances. They also have minimal residues as compared to the solid fuels, because solid fuels produce a lot of ash, but liquid fuels like petrol, you rarely find their residues, like in terms of maybe ash, or what can come out could be the carbon monoxide or those black particles that could be left around the exhaust pipes of automobiles. Then the storage and handling, yeah, you can store them easily in tanks, and of course they require careful handling to avoid spills and leaks that would of course pose threats to fire outbreaks. Uh, of course, thereby destroying property and losing lives. Then the gaseous fuels, we are still talking about fuels classification by state, and we have gaseous fuels that include the natural gas, biogas, propane, butane. The natural gas, in most cases, is methane that you know, and the liquefied petroleum gas that you always have used for for cooking is one of the gaseous fuels. Then butane and propane. Butane and propane, we shall see them ahead. They are alkanes. They belong to a group of hydrocarbons called alkanes. And we will see how you can differentiate them from other hydrocarbons. Now, the characteristics is that gaseous fuels uh, have clean burning, they are easy to mix with the air for combustion, and require pressurized storage. That's why you always find these gases, like for example LPG, in small cylinders, and those cylinders are highly pressurized so that you have a safe release of this gas in a controlled manner, and of course in which it is able to combine with oxygen or air and be able to burn in the presence of heat, and therefore produce the much heat or the reaction that you need. And out of that reaction, it's the heat that you're interested in for cooking, for heating, for lighting in some other instances, and to run generators that some produce power. Yeah, you can find some generators that use gas, and that gas runs their systems, and then these generators are able to produce either DC or AC power that you can use to run your home and other appliances. Then we also find that they are easy to store, since you can store the gas fuels in cylinders and pipes. But then you need to have some leakage detection systems so that you emphasize the safety measures, since they are highly flammable. Gaseous fuels are highly flammable, and you must never store them near fire, near heat, and you must have proper handling. Now let's look at the calorific values, the lower and higher calorific values, and then probably their measurement. So the higher calorific value is also known as a gross calorific value, GCV, and this includes the total heat that is released when fuel is completely burned and water vapor is condensed. So you have a fuel, so this fuel completely burns. There is nothing that is left. So all of it is completely burnt, and then that water vapor that is produced out of the fuel is also condensed. So the amount of heat used to condense that water vapor is also inclusive. So that's why we call it gross. But now the lower calorific value has a net calorific value, NCV, and it excludes the heat of condensation of water vapor. So you'll have the HCV, which is the higher calorific value, minus the heat of condensation, that is the latent heat of condensation of water vapor, and then you'll have the net calorific value. So the measurement, to measure these two calorific values, one, you can use a bomb calorimeter to measure the HCV of solids, and I mean solid and liquid fuels. Then you can use a gas calorimeter for gaseous fuels to determine their calorific values. Next in our discussion, we are going to look at combustion of elements, and of course, we are talking about the fuel. So the fuel that we are talking about, most of it or most of them are composed of carbon, hydrogen, sulfur, and other elements in their mixture. And you also need an oxidizer, which is usually oxygen from air, so that in the presence of oxygen and that fuel, and then maybe heat, you are able to result into an explosion or a reaction that is later on going to release heat, that which heat you're going to use for different purposes. Then the molecular perspective is that combustion involves breaking the chemical bonds in fuel and forming new bonds to create combustion products. For example, if you have methane here in this chemical reaction or equation, you have methane plus oxygen. This is burning, methane is burning in presence of oxygen or air, and you're producing carbon dioxide plus water if there is complete combustion of methane. In case there is incomplete combustion of methane, of course, you will produce some carbon monoxide, water, and then you might have also excess oxygen at the other side. Now, our task in most of uh, the equations, questions and the calculations, we shall be always tasked to determine the amount of oxygen that has been used, one, to have complete combustion, but also what is available as excess air, and also to some extent you might need to calculate the percentage of nitrogen, since now majority of air, it's the biggest component by proportion that is present in air. You'll find that you have nitrogen always at about 70, about 78, 75, over 70 by volume in most cases. And to do that, we shall need to understand what is stoichiometric air ratio and stoichiometric air ratio, then from which we shall go further and discuss the gravimetric and volumetric analysis of the products of combustion. But now, what is stoichiometric air ratio? Stoichiometric air is now the amount of air required for complete combustion of a given fuel without any excess air. It ensures that all fuel is burned and there is no excess air that remains. So the percentage of excess air, we said you can calculate it, and you will need now to understand what has been used. For example, if stoichiometric air requirement is 10 cubic meter by volume, and then you supplied the 12 cubic meter, then that means the excess would be the 2 cubic meter. So the 2 cubic meter, you divide it by the stoichiometric air, that is the 10, you multiply by 100, and that's why you have 20% as excess air in the byproducts of combustion. So among the byproducts of combustion, you can also always find there excess air, and then you can determine it by this method. Now, gravimetric and volumetric analysis of the products of combustion are the ones now that can help us to determine the percentage of excess air in the products of combustion, and also maybe if there is nitrogen, by what percentage. So the gravimetric analysis involves measurement of mass of each product of combustion, weighing the solid residues, for example, ash, and calculating the mass of the gaseous products from known volumes and densities. So you can be able to determine the mass of ash because you will be provided with data about the volume and maybe the density, so that you use the relation of mass is equal to density times volume, and then you'll be able to determine that mass. Then, of course, you can use that to determine other components, because you have one which is standard that is established, and then you can use it through ratios, using the ratios on the chemical reaction or equation. You are able to determine the mass of those products. How about the volumetric analysis? This is the measurement of volume of gaseous products of combustion, often performed using gas analyzers to determine the the composition of flue gases. This can be carbon dioxide, carbon monoxide, and oxygen, of course, which will always be available as excess. Now, understanding these concepts is crucial for efficient fuel utilization and the optimization of combustion processes, thereby minimizing also environmental impact through proper fuel handling and combustion control. Now, I want to look at the several components which, once burnt in the presence of air, they are able to produce energy, or they are able to produce heat. We will find that when you look at the change in HF, Change in HF is the standard enthalpy of formation, and this is the change in enthalpy or change in heat energy when 1 mole of a compound is formed from its elements in their standard states under standard conditions. And we are talking about 25 degrees Celsius and 1 atmosphere of pressure. The standard state of a substance is its most stable form, is in its stable form at 1 atmosphere and specified temperature, usually which is 25 degrees Celsius. Now, when you look at this table, you realize oxygen as an atom, for example, it has the enthalpy, the change in the enthalpy of formation as this one in kilojoules per mole. Then when it comes to oxygen gas itself as a molecule, you'll find that the enthalpy of the standard enthalpy of formation is 0. Why? We see that the substance, the chemical compound of element for which HF is listed, you'll find that the enthalpy of formation value in kilojoules per mole, you'll have a negative value that indicates the formation of a substance from its elements. And this reaction will release energy, that is exothermic. If the reaction is giving you a negative HF or negative value of enthalpy of formation, then that reaction is releasing heat to the surroundings. But if it is a positive, then it is going to absorb heat from the surroundings. So for example, if you are to combine oxygen atoms to produce oxygen gas, then you would need to absorb heat, that is endothermic reaction, to produce the product that you are looking at. Now, if it is existing in its standard form, then the enthalpy of formation is going to be 0. So we are saying that oxygen as a gas in the form of a molecule has a value of 0 kilojoules per mole because it is in its standard state. Oxygen in its standard form is existing as an oxygen molecule, and we are saying at a temperature of 25 degrees Celsius and a pressure of 1 atmosphere, we are able to have that oxygen as a molecule. Then, now water, if we find that we are forming water, liquid water, and its enthalpy of formation is negative, it means in the formation of water from hydrogen and oxygen, we are going to release heat to the surrounding, equivalent to negative 285.765 kilojoules per mole. And if we look at carbon or graphite, it has a value of 0 kilojoules per mole because graphite is the standard state of carbon. So this can exist as graphite or as carbon at 25 degrees Celsius and 1 atmosphere of pressure. So these values that you see here are very essential in calculating the enthalpy of change of chemical reactions using Hess's law. We shall see it as we go ahead. So you can study this table and see this gas of propane. For you to form it, you would to form this propane, you would release a value of 102,900 kilojoules per mole for you to be able to produce that propane from carbon and hydrogen. If you are forming this ethene is an unsaturated hydrocarbon. It has a double bond somewhere. So forming it would require indeed absorption of heat. And this kind of formation of ethene is an endothermic reaction, which is identified or represented by a positive standard enthalpy of formation. So let's go and look at how can we calculate the higher calorific value. How can we calculate the higher calorific value? We need to know that HCV is equal to Q divided by M, whereby Q is the total heat released during combustion and M is the mass of the fuel. Now, what about the net calorific value or the lower calorific value? Is equal to HCV minus the latent heat of vaporization of this water vapor produced. And that's why we get HCV minus this formula, because it helps us to calculate the heat of vaporization of the water vapor. Because you already have the HCV, and so given the values of, for example, the latent heat of vaporization of water, which may be standard, then you may need to determine the mass of water and then the mass of the fuel. So if you have the mass of the water, mass of the fuel multiplied by the latent heat of vaporization, and then you'll be able to produce that heat of vaporization, and then you subtract it from HCV and get your net calorific value. Now, let's look at a number of combustion reactions. We had already talked about methane, which is present in LPG, or the liquefied petroleum gas. We said you have one molecule of methane reacting with two molecules of oxygen, produce the one molecule of carbon dioxide and two molecules of water. So in front here, if we are, for example, balancing, before we have two and these two here, you first have the standard equation, which will be CH4 plus oxygen giving you carbon dioxide plus water. Then in balancing, you'll always come and see carbon atoms, one this side and one this side, and that is wonderful. Then the hydrogen atoms are 4, the other side they are 2. So I look for a value which I write here so that it will make hydrogen atoms 4. So 2 multiplied by 2, you'll get 4 as hydrogen atoms. And those are balanced, the carbon atoms are balanced, and you move to oxygen. Because when you put here 2 on water, then it also affected this one oxygen here. So it becomes now 2 oxygen atoms. Here you have 2 oxygen atoms, they become 4. At the other side, you have 2. So what can you write here so that they become 4? Obviously, it will be 2. And then your equation is going to be balanced. You can't proceed with any equation any calculation, if the equation is not balanced, because you not produce the right amounts of the combustion byproducts. Now, what about the gravimetric and volumetric analysis of the products of combustion? We said you have to measure the mass of the products. For solid fuels, you can collect and weigh the ash. For gases, you can calculate the mass from the volume using ideal gas law, or from known densities, and then you'll be able to calculate the gravimetric proportions of the products of combustion. By volumetric, obviously, you do this on gases, and so here we use gas analyzers. If a flue gas, for example, or the byproduct of combustion, which is gaseous, contains 10% of carbon dioxide by volume, then 5% carbon monoxide, 85% of nitrogen, you use these percentages to calculate the total volume of each component. Yes. So first of all, you write the chemical equation, you balance it, and proceed. The steps in volumetric analysis, obviously you do need to collect the sample, you do the gas analysis, by using gas analyzers such as gas chromatography, infrared analyzers, or non-dispersive infrared sensors, and then be able to analyze the samples that have been collected. Each gas analyzer is designed to detect specific gases and measure their concentrations accurately. So here you might have a sensor that is going to detect maybe a wide range of gases, but you'll find that specific gases have their own sensors. So it will detect the type of gas that is present, but also give the concentration of that particular gas. If it is carbon monoxide, it will tell you it is carbon monoxide, and will tell you also the proportion of carbon dioxide in that sample that is passing by the sensor. Then the volume calculation, you would now do the volume percentages of the different gases. You determine them based on the analyzer readings. Then these percentages are used to calculate the total volume of each gas produced during combustion. So where do we apply the gravimetric and volumetric analysis? So we do this in environmental monitoring to ensure compliance with emissions, regulations by monitoring pollutants like carbon monoxide, NOx, which is the oxide of nitrogen. So it can be nitrogen dioxide, then sulfur dioxide, and particulate matter. Efficiency optimization, also we apply gravimetric and the volumetric analysis for efficiency or optimization to improve the combustion efficiency by analyzing the composition of exhaust gases and adjusting their air-fuel ratio. For example, if you look at the exhaust pipe and determine how much of carbon dioxide is being produced, then it would help you to go back and check your air fuel mixture if it is a petrol engine, and thereby you would be able to improve the combustion efficiency of that engine. Safety and maintenance, you detect incomplete combustion or the presence of hazardous gases to ensure safe operation and schedule maintenance. I would still give an example of an internal combustion engine. If there is incomplete combustion of the fuel, you would produce a lot of carbon monoxide. And therefore, if you detect this carbon monoxide before it goes to the environment, you would work on it and thereby ensure safety and maintenance of your engine and of the system, and therefore, of course, protect the environment from hazardous gases. Research and development is also important because you need to look at the combustion characteristics of different fuels and develop cleaner and more efficient combustion technologies. So let us look at the chemical equations of combustion in simple terms. You'll have a fuel and oxygen, then you produce carbon dioxide plus water plus energy. As simple as that. Because the fuel would be now composed of carbon, hydrogen, and maybe some oxygen from the oxidant itself, of course, which is air, and other substances in the fuel. That makes fuel. So you add the oxygen, then you produce the carbon dioxide, water, and energy. And look at those reactions for methane, for propane, and you can also do one for butane. Then balance and see how best you can be good if such equations came and required you to make some computations. So at the earlier on told you how you can calculate the percentage of excess air. If you have to calculate for excess air, you need to determine the actual air fuel ratio. So you subtract the stoichiometric air fuel ratio. So when you get that value, you divide it by the stoichiometric air fuel. For example, now if I had the stoichiometric value being 2.5, and then the actual fuel I use is 3, then that means I would have 3 minus 2.58 divided by 2.58, I multiply by 100, and that means my excess air would be around 16.3%. So it means 16.3 more air is supplied than required for complete combustion. So ladies and gentlemen, I want to now take you through the general formulae of the common hydrocarbons, which at least you need to have a glimpse of and understand. Now, one is alkanes. So alkanes, these are saturated hydrocarbons, and they have the general formula of CnH2n plus 2. So methane, which is having one carbon atom, so N is the number of carbon atoms. And if it is 1, then you'll be having C1 H2 times 1 plus 2. So this becomes H4, then this is C1. But because putting 1 there would look funny, that's why we don't put it and leave it as CH4, and that is methane. For ethane, those are 2 carbon atoms. So you substitute in this formula, you have C2H6, and that will be your ethane. Butane, propane would be C3H8. Try for butane, try for pentane, and you'll enjoy. Then we look at the alkenes. These are unsaturated hydrocarbons, and they have the general formula of CN2N. Now, if it is ethene has 2 carbon atoms, so I substitute in here, I have C2H4. Propene is 3 carbon atoms. I substitute in this formula, I will have a C3, and obviously I'll have CH6, and so on and so forth. Then the alkynes, those are the 3 bonds. The alkenes have double bonds. The alkynes have the carbon hydrogen triple bond, and the general formula is CnH2n minus 2. So the first one that we can take on is 2 carbon atoms, and that is ethane. So ethane has 2 carbon atoms. So if we substitute it in here, this would be C2H4 minus 2. So that you have C2H2, which is this. Propane would give you C3H4. You try for butane, try for pentane. Then now we have the aromatic hydrocarbons. So these aromatic hydrocarbons are also called arenes, and the general formula is CnHn. These are the simple aromatic hydrocarbons. And the take case in point of benzene, this is going to be C6H6, and that would give you benzene. So we have talked about all those in summary: the alkanes, alkenes, alkynes, and aromatics. So now I wanted to pose these questions, but I think I'm going to make another video so that we're able to proceed from there. Thank you so much.